I am going to show you how to use the 2D simulation in AKABAK to simulate the mode distribution in a room and the frequency response at specific points in the room. So first and foremost, I'm going to show you the 2D mode because the 3D mode is much less computationally efficient. So if you can get away with a 2D simulation and the 2D simulation is useful, then it is definitely preferable to 3D simulation. This is especially true for larger rooms or rooms where you want to simulate to a relatively high frequency. To begin with, AKABAK accepts DXF files for the 2D mode, .dxf files. The biggest problem with this is really just that AKABAK doesn't seem to like a lot of DXF files. For example, if you try to import a DXF file which has an arc in it, the arc will be deleted. If you look at it in a DXF viewer, it's going to look completely fine. The moment you import it into AKABAK, it's going to look wrong. So it's just something to keep in mind. It can be a bit annoying to actually model something for the 2D mode in AKABAK. Now, the first thing we want to do is put it into 2D mode. Currently, it's in 3D mode. We can see we have the x-axis, the y-axis, and the z-axis. So we're just going to go to global, and we're going to go to BEM parameters. And here we can see dimension, and we can see it's set to 3D. We're going to click on this, click 2D, click OK. Now we can see that there's no more z-axis. It's just the x and y-axis, and we're in 2D mode. The next step is to import the drawing of the room. In this case, it's a very simple drawing. It's just a very basic L-shaped room with 6 walls. So I'm going to click on the New Components tab. I'm going to click on this. And then I'm going to be here in the General tab and click Mesh File. This will allow us to import a new mesh file. You can give it a name. In this case, it's not going to be a very complex model, so giving a name doesn't really make any sense, or it's not really necessary. So we can just go to File, click Open, find the file in your File Explorer, and then you can see here it has been imported. Now, one thing you might notice is that size, it says 4 kilometers. This is not quite right. The reason for this is that AKABAK treats the units as meters when they're actually millimeters. So to fix this, we go to Scaling. We set the scaling as 1 millimeter. And now the room is going to be properly sized. Now here we have an image of the room. We can make this a bit bigger. Here we have an image of the room. You can see it has 6 walls. That's all fine. It's completely enclosed, perfectly fine. So we click Apply and we can close. Now we've imported the mesh file and we can work with it. The next step is adding a wall impedance. This is because a real wall is not perfectly reflective. So I'm going to just add a damping coefficient. I'm going to say the damping coefficient is 0.1, for example. This is relatively low, but it's a little bit. And then we can just close this. In this case, you can also give this a name if you want. If you have multiple wall impedances in a single project, that can be a good idea. In this case, it's not necessary. Now, we can go to the BEM mode, or the BEM tab, excuse me. And then we can double click on subdomain. Now, we're going to create a subdomain. And in this case, again, we can give it a name. We're just going to use one subdomain here, so giving it a name is not necessary. We go to Parameters, we choose it to be Interior, we click Apply. We don't actually need to do anything here. The default is perfectly fine. In this case, it's an interior problem. We're only solving for the inside of a room. Now we can close this, and we can click on Elements, Mesh File. This is to add elements from the mesh file we imported into the boundary element model. So we double click on this, and now we'll get the ability to give this a name as well. We don't really care. And then we can go to the Drawing tab and we can see the elements. If we click Apply here, we can see that the drawing has been opened in the Main tab. Now, one thing we have to be aware of is the direction of the normals. All normals should be pointing inwards. So to see the normals, we go to views, and on the bottom here we can see length of normal and direction. Now if we click on this, I'll just drag it a bit, and then we can just close this for a bit. We can see here that there are normals pointing out of the domain. So the normals are pointing out of the room in every case except for this wall, wall number 6. And we have to fix that. So we go back to elements here, we open this again in the drawing, and we mark every element except 6, since 6 is the right way, the normal is pointing inwards, and we click swap selection, or swap select the normals. We click on this and click apply. And now we can see that the normals are in fact pointing inwards. They're pointing in towards the subdomain we're interested in simulating, which is how it should be. So we click apply and we close. Now everything is fine with the room model. The next part is adding some sound sources to the room, as AKABAK, as far as I know, does not support eigenmode analysis. So in this case, we're going to go back to the General tab in the Components menu, and we're going to double click on Nodes. And nodes are basically spatial coordinates. They can be used for many things. They can be used by the internal CAD tool to specify, for example, a pressure source, which is what we're going to do. It can be used as basically building bricks for various geometries in the internal CAD tool. You can use it to define various sound pressure fields and so on. But in this case, we're just going to go to points, and we're going to add a couple of points, 5 in this case. So point 1001 can just be 0, 0, 0. And one thing you'll notice is even if we click apply now, we can't actually see the nodes. So we go up to this menu and we just click here, and now we can see that the nodes are visible. Now there's 5 nodes on top of each other, so it's not easy to read, but it's 1001, 1002, 1003, 1004, and 1005. So in this case, let's set the coordinates for the rest of them. So we're going to set this to minus 1500 millimeters X and 1000 millimeters Y, which is the upper corner here, you can see. And then we're going to set the other one to 1500 millimeters X and 1000 millimeters Y. And we can see that's in the opposite corner. These are going to be our sound sources. So P1002 and 1003 are going to be the sources we use for sound, while P1001, 1004, and 1005 are going to be observation points. We're going to look at the frequency response at these points. So 1004, I think we can place at, let's say, minus 1500 millimeters and minus 1000 millimeters, which is in this corner. And then finally, 1005, I think we can place at 1500 millimeters and minus 2000 millimeters. And then we click apply. And now it's down here. So now we have 5 nodes, 3 of which are going to be used to observe things, and 2 of which are going to be used as sound sources. So now we can click, close the Nodes tab, and we can go back to the BEM tabs in the Component section. Go back to the BEM tab, and then we click Pressure Source, and here we see Pressure Points Nodes. So we click on this, and here we can define some nodes to become pressure sources. So we go to Points, and we add 2, and in this case, node 1002 and node 1003 are going to be our pressure sources. Now, if I click on this, you can see these 2 points have turned red, which indicates that they're a sound source. Oops, I actually forgot something. We're going to open the elements mesh file again. This is the one, this is the walls, the boundaries. And we're going to go to the boundaries section. And we're going to choose type of boundary, and we're going to choose wall impedance. And the reference here is just wall impedance. We only have one wall impedance, which is the one we defined earlier, way at the start. Click apply, and now we can see that the walls have become green. This indicates that they have an impedance specified. So they're not just a hard reflective wall necessarily. They have some kind of impedance specified by us. Now, if we open up the Components tab again, we're almost getting ready to simulate. But before we can start the simulation, we need to decide what we are going to observe. So in this case, in the Components tab, we go to the Observation, and we can click on Fields Shell. Here we can see we have a little cube, which is a field, which is going to show us the sound pressure in the room. But it's a bit small, so we're going to set it, we're going to go to shell, and we're going to make it 4 by 4 meters. And then we're going to click apply. Now we can see that it covers almost the whole room, but there's a little area down here that it doesn't cover. So what we're going to do is we're going to offset it a bit. We're going to just make it minus 500 millimeters in the y-axis, which is clicked on the scaling of position. Okay, apply. So we moved it down a little bit, and now it covers the entire room, you can see. So we close this, and then finally we're going to choose radiation points. Now this is where node 1001, 1004, and 1005 come into play. So we're going to click on radiation points, and on this menu we are going to go to positions. We're going to add 3, and this is going to be 1001. It's going to be 1004. It's going to be 1005. Now we can give it names. So this one can be 1001, for example, and this can be 1004, and this can be 1005. Apply. So now we're going to be generating frequency responses. Now, AKABAK cannot show frequency responses in itself, but it is integrated with a software called VAX, which you should also download when you're downloading AKABAK. And it will automatically open the frequency responses for these 3 points in VAX. I'm going to show you that later. So now everything is set up and ready for simulation. So what we have to decide now are the frequencies we're going to simulate and the mesh resolution. So we go to global and we go to frequencies, and we are going to simulate from, say, 15 to 400 hertz. And let's do 128 frequencies. That's 27 points per octave. That's a pretty high resolution. So the reason I'm only simulating up to 400 is because these are pressure sources. They're omnidirectional. They do not have any directivity. And that means that they're not really representative of a real loudspeaker placed into a room at higher frequencies. So you have to work within the limitations of the simulation so that you don't arrive at false conclusions. So we're going to click OK. And then we're going to go to meshing, also in the globals tab, of course. And then we can define the edge length. So we're going to simulate to 400 hertz. So let's have a mesh resolution of 2.1 kilohertz. That should be plenty. It should be much more than we need. But since this is a 2D mode, it will go very quickly anyways. So it doesn't really matter if we waste just a tiny bit of time simulating something with a slightly higher resolution than what is necessary. Then we also have to go to fixed driving. Now, the reason for this is that we don't have any lamped elements coupled to these sound sources, P1002 and P1003. If you don't have any lamped element models connected to them or coupled to them, then you need to enable fixed driving, otherwise it will give no output. Now, for the weight, unchanged is constant velocity, multiplied by j omega is constant excursion, and divided by j omega is constant acceleration. So none of these are going to match reality particularly well. So if you want to have an accurate frequency response, you should also create a lumped element model. I'm not going to do that here. I'm just going to set it to constant acceleration, which means the driver is in practice flat all the way from 0 Hertz or DC and all the way up to infinity. So I'm going to click apply and then close this. Now, everything is ready for simulation, so we can just go to processing and click calculate all. So first we can see the BM simulation goes really quickly, and then it uses a little bit of time on the fields calculation. And there we go. So now if we go back to the frequencies tab up here, we have a list of frequencies, the frequencies we have simulated. If we click on one, we can see the sound pressure in the room. Now, if we want to have the actual sound pressure, we can go to views and we can go to the level legend. Now, when we have the level legend, we can see the actual sound pressure. So in this case, we can see that the max sound pressure is 39 decibels. It's not very high, but it's the relative levels we're most interested in, really. So if we go back to frequencies, we can scroll through and we can see that at lower frequencies, the pressure goes way higher. And this is due to room gain at low frequencies with a constant acceleration source. But as we move higher in frequency, we can see that the mode distribution gets more and more chaotic and a bit harder to parse. In any case, this is a great way to have a look at what a room does to your response. And you could, for example, create new nodes, or you could move node P1002 and P1003, and then you could rerun the simulation and see how it looks afterwards. So this is a simple way of looking at how in particular, a subwoofer might behave in a room, and where you should ideally place it. Now, we also have some frequency responses for P1001, P1004, and P1005. So I am going to open VAX, and here we can see those responses. Now, I may have applied a bit too much damping. We can see that the frequency response is, well, I won't say it's flat, but it's certainly flatter than what you might necessarily expect. In this case, we can see the frequency response at various points. So we can see that at all points it's kind of rugged and rough, but at some points it's better than others. This was just a basic introduction to how you can use AKABAK to simulate a room, and in particular how you can use it to simulate the placement of a subwoofer by relatively simple modeling. Thank you very much.